Right. 2.55 is where we're going to start to see a number of coding questions pop up. So starting with this one, we want to solve the ground state energy of the harmonic oscillator to 5 significant digits via something called the wag the dog method, aka that is to solve equation 2.73 numerically via code. So first off, as a reminder, equation 2.73 is the analytic solution setup for the harmonic oscillator, where we have d2 psi by d, and then this e variable that I don't know the name of squared is I'm just gonna call it e, is equal to e squared minus k multiplied by psi. And we have, of course, k being equal to 2 times the energy divided by h bar omega. And then e is just this custom variable we use to simplify our expression, which is actually equal to the square root of m omega over h bar multiplied by x. So originally, in the textbook, we solved this via approximation by recognizing that the wave function sort of simplifies down at very large values of this e term. So at large e, psi starts to look something like, or our equation approaches sort of d2 psi by de squared is equal to just e squared times psi, where sort of this e term at very large values of e sort of starts to dominate over the constant, which is k. So in this case, this sort of implies that psi of e has the form of sort of some blank thing at the front multiplied by e to the negative e squared divided by 2, because this is the solution to this differential equation. So this is at large e. And then we sort of stitch this together by saying, okay, well, effectively what this implies is that psi is going to approach 0 as this e term goes to infinity. And what that means is that we don't necessarily know what this is, but we can just write it as some function arbitrarily, and write it as psi of e is equal to some function h of e multiplied by e to the negative e squared divided by 2, where this is a function that behaves in such a way so that this entire thing as a whole is going to in fact go to 0 as e goes to infinity. So this has been gone over extensively in the chapter dealing, or in the section dealing with the harmonic oscillator. So if you're not comfortable with how this is done, please go back and look at that. Otherwise, this question is asking us to solve via wag the dog, which is to vary k until we get a wave function that does indeed go to 0 at large e, and therefore that would be the proper value for k, and that would allow us to find the energy. We are given all of this code in Mathematica, so this problem has basically done most of the work for us. However, the example code is done in Mathematica. Not everyone has Mathematica. If you're a student, you can get it for free, but if you're not a student, maybe you're studying this on your own, more realistically, the code that you'll probably have to end up using is going to be Python. So I will be doing this in Python. Now, at sort of basically what we have to do is we have to recognize that k is already, we already know the proper value of k from the section, from this section in the textbook, which is that it's equal to 2n plus 1. So then we can plug in, n equals 0 for the ground state, and we can set this equal to whatever the actual value of k we find is. And then from there, we can, relate that to this, and then we can find the actual energy. So let's move on to Python. I will switch my screen over to Jupyter Labs, which is my preferred operating environment. And we will go from there. There's actually one thing I forgot to mention before we move on to Python, and it's that the actual specific program we're going to use, or the actual function we're going to use in order to solve this differential equation by force via computer, is something called ODINT. Now, a problem with this is that ODINT isn't actually able to solve second order differentials. So instead, the most typical way to do this is to do a variable change and basically rewrite our second degree differential equation as a system of 2 first order differential equations. So the way that you would do that is basically you would define 2 new functions. I'm going to call them u1 and u2. I'm going to say u1 is just a direct substitution into psi. And I'm going to say that u2 is actually equal to the derivative of psi with respect to e. So if I do that, then I can create this new system of differential equations in terms of u1 and u2 instead of just psi, in which case my new system would be u1 prime is equal to u2. So, you know, the derivative of psi is equal to the derivative of psi. That's basically what that means. And then the second term in this system of equations is going to be the direct substitution into this top expression over here, which if we do it that way, we get that the derivative of u2 prime, or the derivative of u2, aka u2 prime, which is aka d2 psi by de squared, is going to equal e squared minus k multiplied by psi, and psi is u1, so this is equal to u1. And then our two initial conditions, that's another thing that we have to deal with. So note here that in sort of this code, we are sort of given an implied initial condition, which is that u of 0 equals 1 and u prime of 0 equals 0. In terms of psi, this is basically telling us that psi of 0 equals 1 and psi prime of 0 equals 0. This really doesn't matter because we are, remember that our final goal is to find k and therefore the energy. The energy of our harmonic oscillator isn't going to depend on the position or the, sort of the initial conditions. You know, we can start at, if you think of this in terms of classical mechanics, if you have an actual physical harmonic oscillator, the energy of the oscillator isn't going to change depending on whether you start, you know, maybe in the middle or at the left or maybe at the right. That doesn't matter. So in the quantum harmonic oscillator, sort of this logic still holds. The initial conditions aren't important. They're used to solve the actual ordinary differential equations, but regardless of what sort of initial conditions we choose, it sort of is going to give us the same answer regardless. It's just that the general shape of the graph might be a little bit different because the time shift is going to be different due to choosing a different initial condition. That's not important. We're going to just, for our purposes, we're pretty much just going to choose the exact same initial conditions as the Mathematica code does. If we translate this in terms of u1 and u2, then this is basically telling us that u1, because remember u1 is equal to psi, u1 of 0 is equal to just 1, and then u2 is equal to psi prime, so u2 of 0 is just equal to 0. So I'm going to add these over here, so u1 of 0 is equal to 1, and then u2 of 0 is equal to 0. Okay, now we plug this into Python, and I will see you in Jupyter Labs, where we will solve out the systems and get a graph. Okay, welcome to Jupyter. Immediately, let me just make this clear. I am not a programmer. I am a physicist first. So I might not necessarily be able to explain all the in-depth details regarding code. Once again, if you're a physics major, sort of all the code and stuff that you learn is sort of more of a tool to get to the end of the problem than anything. So a lot of the actual notation behind a lot of the code I'm going to put in, I don't necessarily understand why it's done this way, and I won't actually be able to explain it. I just know how to do it, and I know the format for doing it. And realistically, if you're also a physics major, this is probably going to be your experience as well, where you're going to be stealing a lot of code tutorials from online and basically just copying them and sort of knowing the process of plugging it in order to achieve a sort of achieve some sort of goal, but you won't necessarily know the actual in-depth details regarding a lot of these programs. So for Python, I'm going to assume that you already have some basic knowledge of how to use it. If you don't, you might actually want to just skip over these problems because they aren't really that important for actually understanding quantum mechanics. All of the coding problems in this textbook are sort of supplemental because in the real world, coding is indeed a very important part of physics, since you have to plug things into the computer to actually find proper solutions, especially for more complicated systems. But if you don't know Python, you can skip a lot of these computer problems without that much without sort of that much loss of knowledge. So for Python, we're going to have to import some stuff for ODINT. First off, NumPy, because that's just an important thing. We always import NumPy when you're working with math. Import NumPy as NP. Next thing I'm going to do is I'm going to import ODINT. So from scipy.integrate, import ODINT. If you actually want to know more about the ODINT function, or maybe just the scipy.integrate module, by all means, you can look that up online and sort of read up on that as well. And then finally, we want to graph everything. So we're going to import matplot library.pyplot as plot. Import mat. Did I spell everything right? Yeah. Okay, next, we want to actually set up the equation in code. So to do this for ODINT, what you do is you define a function f of u comma e, and I'm going to sort of go over this very, very quickly because there's tons of tutorials online on how to use ODINT. If you're not familiar with how to do it, I would recommend you look up a tutorial online on how they actually solve second order differentials with ODINT. But pretty much we're going to define u as an array, I believe. So we're going to return, and we're going to say, okay, I'm going to define u1 and u0 as sort of my u1 and u2s respectively. And I'm going to say, so if I look back at sort of my system of two differential equations that I've defined earlier, I have u1 prime is equal to u2. So I'm going to define u2 as just u0 with brackets. And then our second equation is u2 prime is equal to e squared minus k times u1. And I'm going to write this as I'm gonna write e as just e. So that weird squiggly variable I'm calling e, I'm gonna call it e in my code. E squared minus k, and then multiplied by u, and then u1 I'm gonna denote as u0. Or sorry, u1 I'm gonna denote as u1, I believe. Oh, sorry, it's the other way around. So u1 is denoted u0, and then u2, which is u1 prime, is going to be denoted as u bracket 1 instead. So once again, I don't know why the notation requires us to do this. I haven't really been able to find anything online as to why this is done this way, but this is just how it's done. If you want more examples, there's plenty on how to integrate second order differentials via ODINT. They all follow this common method of using this bracket notation to dictate our two systems. Next, we need to define our initial conditions, and we already have our initial conditions. It's that, I believe, if I look back on my document, it's that u1 of 0 is equal to 1, and u2 of 0 is equal to 0. So if we define this as sort of an array, then we just get u1 of 0 is 1, and u2 of 0 is 0, like this. Because remember, it's an array with u1 first and u2 second. So these y not 0, or just y0, I suppose, is pretty much a definition, or it's a variable used in the ODINT function, and it's basically, it defines our initial conditions. Now finally, we have to graph everything. So if I want to graph in terms of x, I'm going to set up an x array. I'm going to call it xs is equal to np.linspace, going from 0 to 10 to 200 via 200 steps. So this is basically just me setting up an x-axis array for which to plot on. So this goes from 0 to 10 in 200 steps. So basically I'm plotting 200 points pretty much. And then I'm going to define our ODINT solution, ODINT in terms of our function that's defined earlier, and then y0, and then finally xs, which is going to be our x, which is going to be sort of, our 200 plot points on x. Ys, I'm going to define as in terms of us, going from the start to 0, like this. So basically defining my y-axis, and then finally plotting. So plot xs ys. This is just going to give me my blank plot, and then plot xs ys in terms of r, and then plot x label. I'm going to call this e value, and then plot y label. Call this wave function, and then finally plot show. And then we were told to vary k. Oh, what? Whoops. ODINT. And also, I forgot to define k, so let's do that as well. So we're told to define k starting at 0.9. So if we do that, then what we get is I did something wrong here. What did I do wrong? US is equal to ODINT F Y0 XS. I defined XS, I defined Y0. Return U1. Ah, that's why. It's because I forgot that exponentials in Python are double stars. There we go. Okay, so if we define k as 0.9, we see that this wave function goes all the way to infinity as e goes to infinity. So we don't want that. We want the wave function to go to 0 as e goes to infinity. Now, we do the wag the dog method and apply 1.1 instead of 0.9. And what we notice is that this tail goes the opposite direction now. So we want to find the value for k right in the middle, for which the wave function is going to go to 0 instead of diverging to either positive or negative infinity. Very obviously, this should imply that the actual value for k is directly equal to 1. So let's try 0.99 instead. Once again, it goes up to infinity. If we try 1.01, it goes down to negative infinity. If we keep on going, if we do like 9.99999, for example, once again, or sorry, 0.9999, once again, going to positive infinity, if we do instead 1.0001, once again, this should go down to negative infinity, which it does. So therefore, sort of implying that the correct value for k is 1, exactly. So now let's go back to Paint and actually solve this. Okay, so now we sort of know that k is equal to 1, or very close to 1. And what we also know from up above here is that k is equal to 2e over h bar omega. So this is going to equal 2e over h bar omega. So what that implies is that E is therefore equal to 1/2 h bar omega. And this is exactly equal to the ground state energy for the quantum harmonic oscillator, QHM, or QHO. So this is very promising because we, via brute force on a computer, have found the energy to be equal to the exact same thing we derived when estimating E through the analytic method. We also know, that k is equal to 2n plus 1. So what this implies is that what we've solved so far is the n equals 0 ground state. The next problem will go a little bit more in depth into the same thing, and we're going to be asked to solve for higher energy states. So I will see you on that problem. Okay, 2.56 is kind of just a natural leap, or sort of a continuation of 2.55, and 90% of the problem is solved already by doing 2.55, so I'm actually going to include both of these problems in the exact same video. We are told to use the exact same method and find the first 3 excited state energies, but the key point here is that we have to use a different set of initial conditions for some reason for the first and third excited states. Because remember, originally in 2.55, the initial condition we used was that the wave function at 0 was equal to 1, and the wave function's derivative at 0 was equal to 0. And for some reason here, it's saying that for the first and third excited states, we have to set it up in the opposite way, setting the wave function at 0 to equal 0, and the derivative to equal 1 at 0. So, the reason why this happens is because of the fact that the wave function is alternatingly even and odd between successive energy states. So the problem with having an odd function is that this initial condition is not possible, because an odd function, remember, always has to go to 0 at x equals to 0. If we used, the initial condition from 2.55, which is that it goes to 1 at 0, that's not an odd function. That is an even function. And as a result of that, using this set of initial conditions will only give us valid k values for even states. Whereas using this u equals 0, u of 0 equals 0, and u prime of 0 equals 1 set of initial conditions is going to give us valid k values for all of the odd states. So, because of that, we're basically just going to have to switch around the initial conditions depending on which k value we're going for. And with that, I will meet you on Python. Okay, welcome to Python. We have the exact same setup as we had before. The difference now is that instead of trying to find it about k equals 1, our first excited state is going to be k equals 3, because remember, k equals 2n plus 1. So the first 3 excited states correspond to n equals 1, 2, and 3, therefore k equals 3, 5, and 7. So the first thing we're going to try to find is between 3. So we start with k equals 2.9, and then we do 3.1, and we should see that the graph does indeed switch. Now, remember, once again, we have this extra condition that our initial conditions need to change in order to be valid for an odd wave function, because the n equals 1 state, aka the first excited state, must be an odd function. So therefore, if we didn't change the initial conditions and we just stuck with y0 equals 1 comma 0, which is the even initial conditions, what you're going to see is that if you do k equals 2.9, okay, it goes down. But if I switch to 3.1, it does not switch. So therefore that implies that k equals 3 is not a valid solution for this set. And the reason why it's not a valid solution is because of the fact that I didn't switch my initial conditions to correspond to an odd wave function. So let's switch this around and let's go back to using 2.9. And then we see here now that for 2.9 it goes up, and if we switch to 3.1, it now goes down. So therefore, you can do this up to 3 sig figs, 2.99999, and then 3.00001, and you see that this behavior is the same. Therefore, k equals 3 is going to be a valid solution for k. And we do the same thing for the second energy state, so k equals 5. So we do 4.99999, and remember, this is now an even function, so we have to switch around the initial conditions once again. And we see that for 4.99999, whoops, maybe, I think my code might be frozen. Give me 1 second. Okay, wonderful. My Jupyter just crashed, and because of that, I had to reset everything. But anyway, so now let's do k equals 5. So we plot around k equals 5. That's going to be 4.999. And once again, remember, I've preemptively already switched the initial conditions. These are the valid initial conditions for even solutions, which the k equals 5 solution does, in fact, have to be even, because remember, that's n equals 2. And if we do even, odd, even, right, it's from 0, 1, 2, n equals 2 has to be even. And we see here that it graphs down. Now let's graph 5.0001. And we see that it graphs up. Therefore, k equals 5 is also a valid solution. Next, we want to try it for k equals 7. Once again, that's going to be odd. We have to switch around our initial conditions again from 1, 0 to 0, 1. And then let's try it again, this time 6.999, which is going to be down, and then 7.0001, or 7.001, I guess, which is going to be up. Therefore, it switches right around k equals 7. Therefore, 7 is also a valid solution. Now, it's just a matter of plugging this in, and we will be done. So I will meet you back on Paint. Okay, so now that we're back on Paint, we now know that k equals 3, 5, and 7 are all valid solutions. And we also know from earlier that k is just equal to 2e over h bar omega. So for the n equals 1 case, which is the first excited state, we get k is equal to 3 is equal to 2e over h bar omega. If we want to isolate e, then we get e is equal to 3/2 h bar omega. For n equals 2, which is the second excited state, we get k equals 5 as a valid solution, which is equal to 2e over h bar omega. Therefore, e is equal to 5/2 h bar omega. And then for the third excited state, n equals 3, we get k is equal to 7 is valid. Therefore, 2e over h bar omega. And therefore, e is equal to 7/2 h bar omega. And if you look at this, you'll see that this is exactly the first excited state energy for the simple harmonic oscillator. This is exactly the second one. This is exactly the third excited state. So therefore, we verified it because we already knew this from just doing the analytic derivation of the quantum harmonic oscillator, but we verified it by brute forcing this same sort of differential equation online via wag the dog, or wag the tail, sorry. And with that, we are done with 2.56.